Hello everyone. My today's presentation topic is MMIC Technology Chapter 3. Before going into details of my presentation, I would like to give you a short introduction about me. This is Mehedi-Joni. Currently, I am studying 4th semester in the Department of Electronic Engineering at Kwangwoon University as an master's leading PhD student. Along with that, I am working as a research assistant in Advanced Quantum Nanomaterial and Optoelectronic Laboratory. My academic supervisor is Professor Jion Lee, and my ongoing research project is transitional metal-based electrocatalyst fabrication with material characterization for cost-effective green hydrogen energy production. So, these are the outline of my presentation. First of all, I would like to talk about basic theory of amplifier. After then, I will focus on DC bias injection. Furthermore, I will focus on classical stability and gain. After that, noise consideration, IF amplifier design, and finally, I will conclude my presentation by talking about cascade LAN design and power amplifier. So, in this slide, we will talk about the background and basic theory of MMIC amplifiers. So, the most important aspect of design consideration for microwave transistor amplifier are depending on really, for example, stability, power gain, bandwidth, noise, and DC requirements. So, this section will primarily focus on DC bias injection, stability issues, gain, and optimization. So here we will discuss about DC bias injection. So biasing is a crucial for FET operation in amplifiers. It sets the operating points on the FET current versus voltage curve, affecting factors like gain and noise. There are several biasing methods, for example, and each biasing method have some advantages and some drawbacks. So for example, we can say the standard biasing. It is very much common for the low power application and it uses a source of a resistor. After that, resistor biasing. It is a good choice for the gate biasing due to low gate current and device stabilization. Then cell biasing. It is enable for single supply operation but has slightly higher power consumption and fixed bias mode. Furthermore, active load. It is compact and suitable for the DC coupled amplifiers but reduce gain. So in this figure we can see figure number 1, it is FET current versus voltage curve and the operation system, and figure 2 and 3 it is the network system of DC biasing. And finally the stacked biasing. It is ideal for ultra low power consumption by cascading bias currents through multiple FET stages. For example, figure number 4. So choosing the right biasing method depending on the amplifier specific requirements. It is on chip decoupling capacitor for bias might not be sufficient and external solution may be needed for the stability. So here we will focus on classical stability and gain analysis. So in this slide we will discuss amplifier stability. It is a crucial design factor. There are two types of stability. For example, unconditional stability and another one is conditional stability. So for in terms of unconditional stability, the amplifier won't oscillate regardless the connected components. It means matching network or terminators. This is preferred and focus here. For the conditional stability, oscillations might occur depending on the connected components. So in terms of stability circles and Smith charts, we can understand here that a tool called stability circle helps to visualize stability graphically on the Smith chart. After that, the circle represents a region of stable load impedance, and furthermore, the location of this origin on the Smith charts indicate the whether the stable region inside or outside of the circle. So for example, we can see the figure number 1, it is stable and unstable region, and the figure number 2, it is the unconditional stability. So there is another factor, it is called a new stability parameter, and here we can also introduce a new parameter for the stability purpose for analyzing the stability. So we can see if micro is greater than 1, the circuit is unconditionally stable, and this single parameter simplifies stability assessment compared to the previous method. So here we need to know about the classical stability and gain analysis part. There is some improvement of the stability part. So in this slide we will cover the method of improving amplifier stability and formulas for the calculating power gain in microwave amplifiers. So in terms of improving stability, there are two factors. For example, resistive loading, another one is negative feedback. So what is resistive loading? Resistive loading is adding resistors, series or short, to the input or output can enhance the stability. So the choice of depends on the circuit stability. Circle number we can see here, the figure number 3, and this method affect the gain and noise, so it requires balancing stability needs with applications specifications. So furthermore, the negative feedback. What about the negative feedback? It means the most amplifiers use negative feedback which improve the stability compared to the positive feedback. So power gain, there are some equations for the power gain. We can call it the power gain equations. These equations will define three key factors gain formula used in microwave amplifier design. For example, transducer power gain, what is called GT, power gain GP or operational power gain. We can also say it operational power gain, and after that we can see here the available power gain. It is also called GA. So figure number 2, here it is illustrating something like that, a general microwave amplifier that is showing how these gains can be calculated using this S parameter or reflection of the coefficients. So here we can see the three formulas. One is GT, one is GP, one is GA. By this way we can measure or we can specify this stability improvement. So in terms of noise consideration, in this slide we will talk about the thermal and short noise. So what is the thermal noise? We can see here the thermal noise. Here is some major limitation in the communication sensitivity. There are some key points. I will discuss about the key points. The thermal noise originated from the random movements of charge carriers in conductors. It is also called Johnson noise or Nyquist noise. Thermal noise is a power is proportional to temperature. It means if you increase the temperature, then the thermal noise would be increased. There is one bandwidth, it is called delta F, and delta F, where the delta F is P is equal to KT into delta F. So where K is the Boltzmann constant. This noise power is independent of frequency, making it appear white across a spectrum. This term available noise powder and refers to the maximum transitionable noise powder to load. This noisy resistor can be modeled as a voltage generator in series with the actual resistor. So in terms of short noise, there are some fundamentals. So the short noise arises from the directance of the electric charge, but it is only occurs under two conditions. For example, direct current flow, there is needed to be continuous flow of electron. So secondly, potential barriers, electron must be overcome an energy barrier to contribute the noise. So another two noise consideration, it would be something like that. One is flicker, one is popcorn noise. So flicker noise is a mysterious type of noise. It has a 1/f characteristics, it meaning the intensity is inversely proportional to frequency. Surprisingly, various phenomena exhibit flicker noise, including cell membrane potential, earth rotation rate, galactic radiation noise, transistor noise. So on the other hand, about the popcorn noise, we can see here are some key points about the popcorn noise in semiconductor field. So also it is called burst noise or beatable noise or random telegraph signals. It is shortly we can say RTS. So another key point is less understood than 1 by f noise, and it is shared sensitivity to contaminate with the 1 by f noise found in this kind of popcorn noise found in point contact diodes, junction and tunnel diodes, some resistors, and resistors those are direct or integrated circuit. So in the next slide we will go for the practical design of amplifiers. So we will include here three types of designs. One is IF amplifiers design, secondly cascade L and A design, and lastly power amplifier design. So it is the starting point of the IF amplifier design, and this is the introduction part. And this slide I have included one figure. It is a block diagram of LNB. So this section introduced the IF amplifier with a KU band LNB down converter system, and this is the figure. And the LNB role is converted to high frequency satellite signal. You can see here in the down of the lower intermediate frequency, and there is some specific range. And here what the IF amplifier does, the boost the weakened signal weakened signal to the usable level for the set-top box, and it can operate a system impedance of 75 ohm instead of typical impedance of 50 ohm, and it can compensate the signal loss from the mixer and the filters. It also provides the additional gain with the flat response across the with the bandwidth, and it can maintain the low noise figures, for example not as critical the low noise amplifiers noise figures. So it can also handle the high output power without significant compression. So this amplifier in this figure we can see it, this amplifier characteristic ensure the good linearity and the positive gain slope, the counter attack and counteract signal we can the other parts of these systems. So in this figure we can see the RF signals and LN and filter, and after the mixer and LO, this is the two combination, and the IF amplifier, it is the IF amplifier, and furthermore the we can convert it into the IR signal. And here there will have some indium gallium phosphate HBT technology, and it is related to IF amplifier design. Here are some common information on the high linearity HBT device in the short points. So there are some key parameters we know, and beta, ft and f maximum, these are the key parameters for the breakdown voltage. And the technology, it could be 6-inch indium gallium phosphate HBT with 4 emitter fingers and transistor details, and there will have emitters, base and collectors, and those kind of things will be available there. And the typical operation, 50 microampere current and maximum 160 microampere at the 150 degree Celsius junction temperature would be there. And the fabrication process and optimization for the MMIC technology, capacitor and spiral inductor and resistors via holes and transmissions line will be available for this indium gallium HBT technology. So in this slide, IF amplifier design, we mean here two-step IF design. So in this section, the details about a two-stage broadband IF amplifier design for a KU band L and B. There are some key points, and here I have shown, and figure number 1 it is called simplified schematic amplifiers, and figure number 2 it is lossy matching. So there are some key points we need to know. This is key points are much more important. So for example, goal and to achieve a flat gain response across a bandwidth gap 1 to 2 gigahertz. So circuitry, and there are two common emitter HBT stages, and you can see about the specified schematic amplifiers in the figure number 1. And after that, the biasing, we can use the voltage divider and resistor for stable bias point and maximum output swing. And matching, it employs the lossy matching with resistors. And the figure number 2, we can see here the lossy matching, input matching, interstage matching, and output matching. And there is another key point, it is called stability, a challenge in two-stage design due to potential gain, ripple, and interstage oscillation. So after that, interstage matching. What is the interstage matching? Frequency dependent mismatch and introduced to improve the stability. For example, traditional K factor might not be sufficient for assessing stability here. And secondly, ideal scenario, unconditionally stable transistor would have 50 ohm matched with input or output for maximum power transistor. And finally, the network design. So considering the poles and zeros to achieve the desired interstage matching response. So this is all about the two-step IF designs. So here we can see the fabrication and measurement about the IF amplifier design. So the fabricated two-stage IF amplifier achieved good performance. We can see here the measurement confirmed a gain of 27 decibels, slightly lower than simulation with the consistent response, and the response would be here 1.5 decibel variation across the desired bandwidth, and desired bandwidth would be 950 megahertz to 2 gigahertz. So we can see the figure number 1, the measured S21, and figure number 2, it is showing the P1 decibel. So after that, the amplifier also demonstrated good matching at the band input and output. So figure number 2, we can see here the HBT device, and it is one kind of showcase of photograph of this successful indium gallium phosphide HBT MMIC amplifier chip. So there we'll have a short talk about the Chashkat LN design, about the introduction part, and indium gallium phosphate HBT. This section purpose a new fully integrated image rejection filter for a KU band LNB system. For example, the figure number 1, it is block diagram of KU band LNB. It's built using indium gallium phosphide or gallium arsenide HBT technology instead of traditional silicon germanium or CMOS, with the on-chip tuning via base collector diodes. This design offers excellent performance and maximizes the noise contribution from the filter. So on the other hand, the LNA design utilizes indium gallium phosphide or gallium arsenide HBT technology with specific transistor properties. There are some properties here we need to know: the true emitter fingers, 2 micrometer emitter width, and 20 micrometer emitter length, and beta of equal to 115, and ft is would be 50 gigahertz, and f maximum would be 18 gigahertz 80 gigahertz. The base collector injection diode for filtering and tuning, and this is the overall of indium gallium HBT characteristics. So this slide will talk about the Chashkat LNA design and fabrication about the measurement. So LNA design prioritizes the low noise and power consumption. Here it is breaking down. First of all, the transistor Q1 and Q2. Two emitters fingers for the maximize the base resistance, specified bias current 6 mA for low noise and power efficiency. Q2 acts as both a minor and driver transistor. After that, the bias circuits. So uses resistor R2 and R3 and transistors Q6 and Q7 to maintain the proper bias for the Q2. R3 maximizes the noise injection from Q6, and after that the image reject notch filter. So it is uses a fully integrated series resonator Q3, Q4 and L5 and L3 and capacitor. We can see the figure number 1, all the things, and created zero impedance at Q2 emitters at notch frequency surfacing the unwanted signal. Q tuning. What is the meaning of Q tuning? It means adjusting the minor current of Q4, control the notch depth using negative resistance, and it would be here the large transistor Q3 maximize noise contribution during the Q tuning. In capacitor C4 improve the linearity and reduce the coupling between tuning methods. And capacitor C5 decouple the control voltage from Q3, and tuning is achieved by adjusting the capacitance C bar of the base collector induction diode D1 to D10 using the control voltage B constant. So this region offer a tunable image rejection filter with minimal noise impact, all integrated on the chip. So on the other hand, the fabrication and the measurement. So about the fabricated LNA chip, it is tested and achieved by the SOA over 6 decibel gain in the desired band with the notch of and 20 decibel image rejection below 9.25 gigahertz, and there would be with a notch on, and it could be slightly lower gain across a wider bandwidth, and deep notch would be on some range minus 66.2 decibel to 8 gigahertz, 8.55 gigahertz. And furthermore, noise finger variation between 0.2 decibel to 4.8 decibel, small gain variation into 1.2 decibel to 1.6 decibel between notch and off and on states. And this is about the fabrication method and the testing method of this LNA chip. So we need to focus on their power amplifier design, and we'll talk about some introduction part about this and the indium gallium phosphide HBT about related to power amplifier design. So this section will discuss the design of a 1 watt power amplifier by PA for CDMA application using indium gallium phosphide gallium arsenide HBT technology. The PA prioritizes achieving an output power greater than 31 decibel M. Here's the breakdown of this multi-stage design. For example, each stage is built using cells, and the first stage utilizes F into 2 into 20 cells, and the second stage is compressed into 12 transistors, and the third stage is amplified into 48 cells. As we can see here, the figure number 1, the 3-stage power amplifiers. So on the other hand, the HBT, indium gallium phosphide HBT technology. A power amplifier PA acts like a power converter, taking DC supply power, PDC, and turning into a microwave signal power P output based on an input signal P input, as shown as the figure number 2, PA operation. So here would be drain and collector efficiency. It would be something like that P output divided by P DC, and there is some equation, and this might not consider of the significant input power required. Then the alternative efficiency metric is the power added efficiency, what is called PAE, and it could be P output divided by P DC plus P input. These consider both input and DC power. And in this section we also mention the P1 decibel, IP3 and OIP3, which will be explained on the next chapter. So in terms of power application design, we will talk about the load pull method. The load pull method, the design of a power amplifier based on the load pull, is the most empirical approach. In its basic form, an output tuner is adjusted to maximize the 124 the output power, and the tuner is removed, and then the independent measure of the analyzer. And the load pull method is a practical approach for designing of the amplifiers. Here is the process. First of all, the tuner optimization, and secondly the impedance measurement. So in terms of tuner optimization, an output tuner is adjusted to maximize the output power, and the impedance measurement, it is the tuner is removed and it is the impedance measured in the repeat and plot. Step 1 and 2 are repeated for the various tuner setting and creating a graph for the constant power levels on a Smith chart. And furthermore, the automation is key. Automatically, this process is crucial due to the many test conditions that is needed to be verified, input signal and bias and frequency, for example, and finally the benefits. It could be provides the data for the optimal load selection considering performance trade-offs, and it is also useful for the active device model extraction and verification. So there are some challenges as well as, so it requires an automated load pull measurement bench, and it is selecting by the right physical device to avoid complex de-embedding procedures. And these are the some challenges in this load pull method. So in this last slide we will talk about the power amplifier design, about the fabrication and measurement techniques. The fabricated three-stage power amplifier, I mean PA, is designed for CDMA applications. Here the key test results are following below. So in terms of the gain, it is achieved a maximum available gain, and S21 gain is greater than 25 decibel within the CDMA band. So after that, the stability and the stable operation throughout this desired bandwidth with a stable factor exceeding 1. So output power 1 P1 decibel is measured at 34.59 decibel, and it can be achieved derived from the measured intermodulation distortion values. So finally, the efficiency PA, power added efficiency, it is shown as the function of the input power. We can see the figure number 1, the characteristics of PAE, and finally the chip on board. The fabricated three-stage PA chip is shown here, and the final output stage consume more current, and so bonding wires are used in this section. So a PCB board was used for this measurement. Thank you everyone for watching this presentation. If you have any question, then you can ask me in the comment box. Thank you once again.